Hi, my name is Madison Stephens, and this is my presentation for Lab 4 pertaining Faraday's Law. Alrighty, so this is my introduction. The purpose of this lab was to understand Faraday's Law in a more experimental manner by collecting observational data and then comparing it to computational models. For the observational portion, we're collecting time-based data on how fast a bar magnet will fall through an aluminum tube, and the computational portion will write Python code in order to simulate that process, and then we'll find a number and compare that to our observational. A brief preview of the results. Our observational found that 1.25 seconds was the amount of time it took for the magnet to reach the exit of the tube, and then for computational it was 1.19. So some important models and setup information. I have a diagram down at the bottom that kind of shows the magnet's going to just fall through the aluminum tube and our entry and exit, and we're just going to find the total amount of time that it takes to fall through that aluminum tube. There will be a total of 5 trials, and then we'll find the average of those 5 trials. Each time, like I said, the magnet is dropped. The system is considered the magnet and the aluminum tube. The surroundings is a stable environment. We're going to set up a camera in order to track the time and to make reasonable measurements so we can see exactly when it enters and exits. The initial conditions: the magnet begins at rest, being held at the top of the aluminum tube, and time starts at 0. So some important physics fundamentals: Faraday's law, which relates the rate of change of magnetic flux to EMF induced in a conductor. Ohm's law, which relates current, voltage, and resistance. Lenz's law: induced electric current flows opposite to the change that induced it. Magnetic fields, magnetic flux, and momentum, also similar to what we saw in Lab 2. And to the right, there is a kind of example of Faraday's law with a coil and a magnet. And then to the bottom is some of the equations I found helpful in kind of our understanding throughout this lab. So this was my observational data. We had the tube length at 0.3 meters, tube width at 0.006 meters, the inner radius at 0.02, outer radius at 0.03. The magnet's mass was 0.025 kilograms, and our magnet dipole moment, or mu, is 3.21. And then to the right here is a table of all of my trials. Obviously, like we said, the initial condition, time starts at 0, and then these are the times at the exit, and then the average time is down in the bottom corner, which we measured at 1.252. And so these are some important checkpoint questions that were in the instructions. Why can't we use a ferrous tube such as a steel pipe? So if the tube were made of iron or contained iron, this would mess with the magnetic properties that the experiment would have. By using an aluminum, there's no magnetic field brought on by the tube, and it allows the magnet to fall freely without any sort of attraction. When the magnet is falling through the tube, as it falls slowly compared to a non-magnetic object. Thus, if I were supposed to drop a pen down the tube, it would fall straight to the ground. The magnet fell a little bit slower, almost like there was some sort of force acting upon it. So I have 4 slides containing my code. This first one is just defining parameters and creating the simulated aluminum tube. And then this one, we finished creating the tube and the bar magnet while setting the initial conditions. This is kind of some of the code that we use to find the magnetic flux and the gravitational force. And then here we're finalizing all those calculations and plotting the velocity versus time graph. So these are our results visually. We found, first it popped up with the current rings falling down the magnet or the aluminum tube, and then we have our velocity versus time graph, as well as that time and tube down at the bottom. So some what-if questions. If the resistivity of the conductor were reduced as close as possible to 0, how would the dynamics of the falling magnet change? So if it was reduced, the current would then increase. We know this because of Ohm's law, and then it would cause the dynamics of the magnet to change by allowing it to fall slower, therefore making the time to fall larger. It could even increase the forces so much that the magnet would barely even fall. If there were holes and slots and cut into the tube, the ring currents in the model would decrease. The magnetic force and current would reduce, allowing the bar magnet to fall through the tube even faster, and reduced current leads to less of braking force or resistive force. Conclusions, possible sources of error. Obviously, we have some human error, but overall, I think the numbers were within reason, and it really helped us understand Faraday's law. Thank you, and the link to my code is in the bottom.